Here we have a plain uniform lamina. This means that its thickness, which is into the screen, is the same everywhere. It's uniform, and its density doesn't vary either. Its density is the same everywhere. We will be ignoring its thickness. We will assume that its thickness is so small that it's negligible. Now, the point G here is the center of mass of this lamina. To find the center of mass, we must find both x bar and y bar. To get x bar, we have to get the sum of the moments of little pieces of this lamina about the y-axis. So we imagine dividing this lamina up into tiny little pieces and getting their moments about the y-axis. So the distance to the y-axis will be the x value of each tiny little piece, whose mass is, well, we can call its mass delta mi. Now when I say distance to the y-axis, I really mean the coordinate, the x-coordinate of each little piece. Now as you can see, for this particular lamina, all the x-coordinates are going to be positive, but of course the lamina could be like this, so some of them will be positive, some others will be negative. That's not the picture here, but of course it doesn't have to be like this. So for this picture, xi happens to be positive for all pieces of this lamina, and then we have to sum up all those little moments. So each moment is going to be delta mi times xi, where the delta means a very small piece of this lamina. Its mass is delta mi. So we would have to sum all of these, and then we have to divide by the sum of all the little mass elements. Well, of course, the sum of all the little mass elements is just the mass of the lamina, and if the mass of the lamina is big M, well, this is what we get. So this will give us the x coordinate of the center of mass. That's x bar. Of course, we have a similar formula for y bar. We're taking moments about the x-axis, so we're getting all the yi's. Well, it's y bar for point G, but say for this mass element here, we can call its coordinate yi, its y coordinate yi. So we're going to get sigma delta mi times yi divided by sigma delta mi. Well, that's just big M, the mass of the lamina, and that's our y bar. Now, since we're dealing with a uniform lamina, we have the notion of the mass per unit area of that lamina. So a unit area could be 1 square meter, or it could be 1 square millimeter, or whatever. Well, the normal SI unit would be kilogram per square meter. We don't have to worry about kilogram per cubic meter because we're ignoring the thickness of the lamina. So we're taking unit area of it, which is 1 square meter. Well, 1 square meter could actually be much bigger than the particular lamina, but that doesn't matter actually. Imagine that we have 1 square meter marked out here. Its mass will be denoted by rho. So rho is not a density in the usual sense of the word. Density is mass per unit volume. We will be using rho in our calculations. So for example, if we know the area of each little mass element, if we know what the area of this is, we can multiply the area by the mass per unit area to get the mass of this element. So we would multiply the mass per unit area by the area of this element, which is, we can say, is delta AI, A for area. So if we know rho, which is the mass of 1 square meter, well, if we multiply that by the area in square meters, we will get the mass of that element. Of course, delta AI will be some very tiny mass element. It will be much smaller than 1 square meter, that's for sure. So anyway, we will end up with units of kilograms, because if rho has units of kilograms per meter squared, and if we multiply that by a quantity with units of area, well, that's meters squared, you can see that we end up with something with units of kilograms, which is what we want. We want the mass of this element. So just to reiterate what I was saying in a different way maybe, if rho is the mass of 1 unit of the lamina, then 2 units will have a mass of 2 rho, of course. 3 units will have a mass of 3 rho, and so on. So if our mass element has area big A, well, I call it delta little ai, but okay, let's say it's big A, then its mass will be the area of it times the mass per unit area. So that's just reiterating what I said. Let's take this example here. We have the line y equals 3x, and we have its mirror image in the x-axis, this line here. So these two lines and this vertical line form a triangular lamina. Now by symmetry we can see that the center of mass must lie on the x-axis. So y bar must be 0. Now let's get x bar. Let rho stand for the mass per unit area of the lamina. So this idea of mass per unit area is very useful, because when we're getting mass elements we just need to consider the area of the element, and we can work that out from the geometry, and we multiply that area by the constant rho to get the mass of that element. So in this case an element of mass will be shown parallel to the y-axis, and we'll be calculating moments of this about the y-axis. So remember, to get x bar we need to sum each mass element times its x coordinate, so that's its distance to the y-axis. So xi, say this is the ith element, so xi is its coordinate. Now we want it to be a tiny little mass element, so we want its thickness to be tiny. We'll call it delta x, and then we take limits. We'll let delta x go to 0. So what's the area of this mass element? Well, it's approximately in the shape of a rectangle, and that approximation will get better as delta x gets smaller and smaller. Okay, what are the sides of this approximate rectangle? Well, if the position of this point here is xi, then this distance here is just the y coordinate of this point here, and this is a point on this line, so this distance is 3x. Well, okay, the y looks like we're looking at this point, but this point is so close to this point that we're only looking at the coordinates of this lower down point, and these points will coincide in the limit as delta x goes to 0. Now of course the distance down here by symmetry is also 3x, and that is positive, by the way, because x happens to be positive here, so we really are getting distances here, and this distance here is 3xi also, so the total distance is 6xi, and we have to multiply that by the thickness, so we multiply the sides of the rectangle together. So one side is this here, which is 6xi, and the other side is just the thickness, which is delta xi. Well, we just write delta x because all the elements that we will deal with will have thickness delta x. Now I'm using two different symbols for delta here, but that doesn't matter actually. We could just use this delta symbol here, I suppose. Now to get the mass of this element here, which we can think of as a point actually, even though it's not a point, it's elongated, but we can think of it as a point with distance xi to the y-axis, we need to multiply its area, which is this here, by the mass per unit area, that's rho. So we want to get rho times delta ai. So what is rho? Well, we're not given rho here. Actually, it doesn't matter what the mass per unit area is. The position of the center of mass doesn't depend on that, no matter how big or small rho is. What we want to do is get the total mass in terms of rho, because the total mass is going to come into this calculation. You know that we have to divide by the total mass when we're calculating x bar and y bar. So to get the total mass we want the mass per unit area, that's the mass of 1 unit area of this, and you know we need to multiply that, the mass of 1 unit area, by the total area, which I'll call A. So big A is actually the area of the total. So what's the area of this triangle? Well, the height of it is from 0 to 1. The height is 1. What's the length of the base? Well, this point here has coordinates 1, 3 times 1, 1, 3. So that's 3 and that's 3. So the total base is 6. So the area is half the base by the height. Half times 6 times the height of 1. That's 3. So we have 3 row times 3, or 3 row. So to calculate x bar, as we saw before, we multiply each mass element by its distance from the y-axis, and that's going to be xi. And then we divide that by the sum of all the mass elements. Well, that's just the total mass of the lamina, which is big M. So now, what's delta mi? Well, we get that from up here. Delta ai is 6i times delta x. 6xi by delta x, as we saw already. That's just the area of this rectangular element, which we can think of as a point mass actually. Distance xi from the y-axis. So we multiply that area by rho, the mass per unit area, to get the mass of this little mass element. So we have this quantity here, 6 rho xi times delta x, and that's multiplied by xi. And all of this is divided by big M. Well, big M is the same as 3 rho. So as you can see, the rows cancel. So as I said earlier, the position of the center of mass doesn't depend on the mass per unit area. Now, when we multiply the xi's, we get xi squared. I'll drop the subscript I that indicates that we have different strips. So the ith strip is the one shown in the picture. But when we're taking the sum, we can say we're summing from x equals 0 to x equals 1. So the first strip is about here at x equals 0, and the last strip is at x equals 1, roughly, very nearly at x equals 1. So now we've found an approximation to x bar. This is not exactly x bar because, as I said, these strips are not exactly rectangles. To make this approximation exact, we have to make delta x go to 0. And we know from previous videos that the limit of a sum is an integral. So this sigma is replaced with an integral sign. We integrate from 0 to 1, 2x squared, and we replace delta x with dx. So if we had any subscript xi, we just drop the subscript. I could have shown it here, but actually I can't show it here because it's not consistent with this notation. We're not summing over I here, we're summing from x equals 0 to 1. So we can't have a subscript here. But we have to change the notation to this so that we can introduce the idea of the integral. Now this is a simple integral. If we integrate 2x squared, we get 2/3 x cubed. And for our limits, we end up getting an answer 2/3. X bar is 2/3. So that's this point here roughly.